In the last video, we talked about how the standard state cell potential is equal to the standard oxidation potential plus the standard reduction potential using half-cell reactions. And it's important to note that we're talking standard state conditions, that is 1 molar concentration solutions, we're talking about 1 atmosphere gas pressures, we're talking about pure solids and pure liquids when we talk about standard state conditions. And we saw at standard state conditions that when we have copper and zinc solutions separated by a wire, we would find that we would expect to have a 1.1 volt solution provided that the copper was sitting in a 1 molar copper solution and the zinc was sitting in a 1 molar zinc ion solution. However, what we saw in last chapter was that reactions don't occur at standard state conditions. That is, they're simply a reference point. And that the standard cell potential is just like the change in Gibbs free energy. In fact, we'll see here in a few minutes that the standard Gibbs energy can be related to the standard cell potential. But what we saw was that the Gibbs energy is equal to the standard Gibbs energy plus the gas constant R, the temperature T in Kelvin, and the natural log of Q, which is the reaction quotient. That is, products raised to their stoichiometric coefficients divided by reactants raised to their stoichiometric coefficients. Well, much like thermodynamics, electrochemical cells also follow a similar type of equation. This is known as the Nernst equation. The Nernst equation says that the cell potential is equal to the standard state cell potential minus RT over NF, where N is the number of moles of electrons transferred and F is Faraday's constant, times the natural log of Q, or again our reaction quotient. The Nernst equation is basically an electrochemical version of our Gibbs energy equation that we saw in the last chapter. So E equals E cell minus RT over NF ln of Q. So how does this relate to Gibbs free energy? Well, we can relate standard cell potentials and standard Gibbs energies through the following. The change in Gibbs energy is equal to the negative value of the number of moles of electrons transferred times Faraday's constant F times the cell potential in volts. Now, here's what brings it all together. For the last couple of chapters, we've been studying different perspectives of the same topic, that is, energy. Equilibrium, Gibbs energy, and electrochemical potential are all related to each other. And this is a nice diagram that ties up everything. You can see that the Gibbs free energy is equal to negative NFE, but you can also see that the change in standard Gibbs free energy is equal to negative RT ln of K. That is, the equilibrium constant is equal to the point where Gibbs energy runs out. The Gibbs energy is equal to 0 when the standard Gibbs energy is equal to the negative value of RT natural log of the equilibrium constant. We also see, similarly, that the standard cell potential is equal to RT over NF ln of K. That is, equilibrium occurs when reactions no longer have energetic drive. And we've talked about this before earlier on in the course of the semester, but this does a rather nice job of tying everything together. Now, this relationship ties in essentially 5 chapters worth of material here. And so knowing how these 3 concepts relate to each other is the major thrust of what we've been studying all semester. Now, electrochemistry has one other aspect to it that we don't normally think about, and that is non-spontaneous reactions. That is, reactions which we would predict never occur, we can actually get them to occur by a process known as electrolysis. Electrolysis is where we take a non-spontaneous reaction and we drive it to occur by supplying it its energy in the form of electrons coming from an outside source. That is, we take a reaction and we supply the electrons by plugging it into a wall outlet. Now, these reactions are not efficient, they take a lot of time, but it is possible to have a non-spontaneous reaction occur provided that you give it energy. And so we can do things like plate out aluminum from a solution of, well, aluminum solution. That is, we can get aluminum metal to come out if we supply current to aluminum ions. And I'm going to leave it with this last slide here, and we'll want to explore in a little more depth when we actually do an electrolysis problem here. But this basically tells you everything you need to know about how to go to how many grams of something like aluminum you could get out by applying a certain voltage for a certain amount of time. And again, it's probably best just to reference to the problem-solving video when you actually come time to solve for this type of problem.